Hello and welcome to Lecture 12, Part 3 for Life in the Universe. In this video, we'll be continuing with Unit E. And at this point, we're going to start looking at light, and in particular by looking at lights as particles and waves. So I guess we should first kind of take a look at what's really the difference between a particle and a wave. So right here at the top, I got a picture I found on a minor league baseball team's website. This player, one of theirs, I think, hitting a home run. And let's say we want to try and to describe the behavior of that ball's trajectory as I guess it comes in from the pitcher, hits off his bat, and then goes on out over the right field fence or whatever. Well, even though that ball does have some extended structure, and that will have some effect on how, say, it's interacting with the air and so forth it's traveling through, we can still do a very good job of describing that ball's behavior by ignoring any structure that it has, just treat it as a mathematical point, as long as we know its mass and we know the forces acting on it. And actually, we could even treat the air resistance to some degree accurately without worrying about those details of its structure. So that's a particle, something that we don't need to worry about any size it has. Okay, but let's say after it goes over the right field wall, it goes splash in a pond, and then we've got this disturbance on the pond surface moving out from where it landed. And now we want to describe that disturbance. Well, because here we have a situation where you have some regions like right here where the water surface is depressed, other regions like right here and right here where it's raised. The very nature of this means we can't consider this disturbance just as a particle, and we have to consider it as an extended entity, in this case a wave. And so that's kind of the point about the difference between them. Well, back in 1801, an Englishman named Thomas Young did an experiment with light called the double slit experiment. If you're interested, you can look it up, learn some more about it. Anyway, the results of this experiment show that light must be a wave. And once this was recognized, everybody said, yay, Young has solved the problem, light's a wave, we're done. Not so fast. By the late 1800s, it was clear that there were some other experiments you can do with light that you couldn't make any sense of with the wave idea. In fact, the classical wave theory predicted things that weren't observed and couldn't predict what was. But then between 1900 and 1905, Max Planck and this guy named Albert Einstein, you probably heard of, showed that the result of those experiments only makes sense if light is a particle. So what's going on? Is it a wave or is it a particle? And the answer is that the concepts of particle and wave, as we developed them in that first slide with the baseball and the water waves, thinking of things happening at the macroscopic scale, kind of large scale things, those concepts are not directly applicable at the scale of microscopic things, things atom-sized and smaller. And that to actually properly describe how anything at that small scale works, you really need to kind of have combinations of both wave and particle properties. And that's what quantum mechanics does. And this isn't true just of light, it's true of everything at that scale. So for example, electrons, you probably have always heard that they are apparently fundamental particles. And yes, it makes a lot of sense to talk about electron as particles. But you can do an experiment with electrons that's exactly analogous to Young's double slit experiment. And the results of that experiment show that electrons are waves. Well, in any event, at least part of the time, we're going to be thinking of light as a particle. And if we're going to think about light particles, we need a name for those particles. And so the word we use for a particle of light is a photon. And when we need a one-character symbol to indicate a photon, we use the Greek letter gamma. Looks kind of like a G, but it's, looks kind of like a Y, but it's the Greek version of a G. Or the G is the Roman alphabet's version of a gamma. Be an equivalent way to think about it. Okay, so some other properties of waves. So you've got this wave propagating from uh, left to right. The size of a wave is conveniently expressed by the distance from one crest to the other, which we call its wavelength, symbol for which is a Greek letter lambda. And anyway, the lambda, which is a Greek version of an L, looks kind of like an upside down Y. Another useful thing is the frequency of a wave, which two ways you can think about it. One is just how many times the wave waves, so goes up and down, completes a cycle per second. Or if you're standing there and watching the wave go by, the frequency is also how many crests of the wave pass you per second. We are going to use letter F for frequency. And the standard unit of frequency in the SI flavor of the metric system is the hertz. Capital H, lowercase z is the abbreviation. And 1 hertz is just simply 1 cycle per second. So this morning, a good bit earlier than I would have preferred, as I stayed up too late last night, my clock radio alarm went off. And it's set to WFCR, our local NPR station, which broadcast at a frequency of 88.5 megahertz. And mega in this context means million. And so that means that the transmitter that WFCR uses produces radio waves that oscillate 88.5 million times per second. Okay, now a couple of interesting things about the wavelengths of visible light. One is that they're small, just a few hundred nanometers, and 1 nanometer is 10 to the minus 9 meters. Sometimes also see angstroms, and angstrom is 10 to the minus 10 meters. So multiply these by 1,000 or by 10 if you want to convert to angstroms. But also, not only are only a few hundred nanometers, but the range is very small. Visible light only varies from about 400 to about 700 nanometers, which is a quite small range. And as less than a factor of 2 variance, and that's all our eyes can see. Now, the speed of any wave, whatever type it is equal to the product of the wavelength and the frequency. We often use the symbol C for that, especially when we're talking about light. And it turns out that light, along with all other types of electromagnetic waves, travel at a speed of 300,000 kilometers per second, which as far as we can tell is the fastest speed there is. Now, let's link photons to the wave properties. It turns out the energy carried by a single photon is equal to a constant known as Planck's constant, whose numerical value is given here, if you care. It's a fundamental constant of nature, times the frequency, or Planck's constant times the speed of light, which is also a constant, so everything up here is a constant, divided by the wavelength, if you'd rather think in terms of wavelengths. So what that means is that if you think in terms of frequency, because the energy and the frequency are directly proportional, high frequency means high energy, low frequency means low energy. Again, talking about the energy in individual photons. Because the energy is inversely proportional to the wavelength is in the denominator, the bottom of the fraction. That means that long wavelength means you have a low photon energy, a short wavelength is high photon energy. And this should make some sense intuitively, because if you look at the wave I'm going to try and make here with my hand. Okay, so this is a low frequency, long wavelength wave. And I don't need to expend a lot of energy to wave my hand this way. Okay, this is easy to do. So on the other hand, or same hand, just doing something else, traveling same speed, but now at a higher frequency and with a shorter wavelength, I have to expend more energy to wave my hand like this. And in fact, I'm already getting a little annoyed at doing it. So I'm going to go back to my easy low frequency, long wavelength, low energy wave. All right, so that's an extremely crude analogy, of course, with what photons do, but it at least should make intuitive sense that frequency, wavelength, and energy are plausibly connected this way. All right, so here is our tenant secret code for this video. This is a picture that was taken by Cal Cudworth, my PhD thesis advisor, back in 1992 when I was a graduate student. And we were attending a conference at UC Santa Cruz on the globular cluster galaxy connection. And so this is in Santa Cruz Bay. This is otter that we saw swimming around, and it's kind of hard to tell at the resolution of this picture. If I remember correctly, to the extent I remember what one individual otter was doing 28 years ago, he was eating a crab, but I think it's the only otter I've ever seen in the wild, so my memory probably is decent on that. So otter in Santa Cruz is our code for this video. And with that, that concludes this video and concludes this lecture. I'll let you know when the lecture 13 videos are available, but in that lecture, we're going to do more with light to finish up Unity. So until then.